But then typically this kind of relay driver and a contactor is not used for driving small electric motors. So with the small electric motors, I mean something like, I'll show you from here. I opened the website of one distributor supplier in Finland, so the texts are in Finnish. So these are small electric motors with the maximum power 10 watts or 20 watts. So there is always a motor and a gear, because the motor is rotating like 6,000 rounds per minute, and you typically don't need that rotational speed, so you need to put there a gear. So in all these motors, you have a gear as well. And then the small motors are, let's say, up to 500 watts or something like that. That's 240 watts. And then the drivers for this kind of motors are typically something like this. In here, I have also taken a company from Finland. So in Finland, in Turku, they are building these, designing and building these, or manufacturing these motor drivers. So the microcontroller is connected on the, let's say, the input circuits on this motor driver, and the motor driver is driving the electric motor, taking the power from the power supply and then external high power supply, and then driving the motors. There we can see power transistors, which are used for controlling the current for the motors. And then that element here is a heat sink. So it's a piece of aluminum dissipating extra heat from the transistors. There is this is not a circuit diagram. This is more like an, So we can have a look on this block diagram of that motor driver. So there is the electric motor. So this is the printed circuit board for that motor driver. And there is the electric motor outside this printed circuit board, of course. So there is a, let's say, 200 watt motor somewhere over there. Okay, they say that maximum current, maximum voltage is 58 volts, and then maximum current 25 amperes, or maximum 5 seconds 50 amperes. So you can put their 1000 watt motor in there roughly. And then these are the transistors for the output. And then there is something which is a pulse width modulation. So the motor is controlled with the pulse width modulation. And the pulse width modulation, I mean, that's defining what is the speed or the torque of the motor. And then the pulse width modulation gets its control from here. And then here we set if we are driving forward or reverse direction. So reverse, forward, either reverse or forward. And then we set the speed. So there is a speed setting. So we can also drive this from the microcontroller output. We set a speed in here. And then this is a level adjustment or the scale for the speed. And then there is a logic in here, and it's controlling this pulse width modulation unit in here, which is controlling the output in here, and that's driving the motor. So that's rather typical way of driving small electric motors. So a motor control board, and then you drive this kind of electric motors. And then we study how that is done. little bit by driving a motor with just one MOSFET transistor. So with our microcontroller, we are controlling just one MOSFET transistor to drive a motor. So our microcontroller is then taking the tasks of these reverse, forward, speed settings, and so on. And we're driving with the pulse width modulation, the transistors, which are then driving the current to the motor. So we go back to the lab instruction sheet, and then into this section here we have the relay drivers, and then after that we have there is a MOSFET. MOSFET is a transistor, so metal oxide semiconductor field effect transistor. That's the symbol. There is the gate, there is a source, there is a drain. The source is like source of the electrons. So electrons are flowing from here up here. So the current is flowing. The current is opposite direction as the electronic flow. So current flows from the drain to the source. And the gate is controlling. From the gate, we control if there is current flowing or not. We can open and stop, or we can start and stop the current in this circuit. And from the symbol, we can see that when there is like this is like dots in here, there it's in initial state, it is not connected. So if there is no gate voltage, the drain is not connected to the source. But when we connect a voltage on the gate, like our logic 3.3 volt, the transistor will be conductive. And it is connected like this. So this is the motor voltage supply plus terminal, for example, 48 volts. There is the motor. The current flows through the motor, through the transistor to the ground. It's quite typical that the motor is here on the higher side and the transistor is here on the lower. It's more economical to produce the transistors which are here on the, let's say, on the voltage, lower voltage level than the motor. And it's easier to control because with 3.3 volts from the microcontroller output, the difference to the ground is 3.3 volts. And we can control the MOSFET gate with that one. So when we put the true or false from the microcontroller output, the false would be the same potential as the ground. And the true would be 3.3 volts compared to the ground here. It would be more difficult if the transistor would be here on the positive voltage.